presentation, I'll cover a part of my research work on the impact of boron rich layer on anti-crystalline silicon solar cells. And I'll try to cover the background of choosing this research topic, the motivation behind, and the open sources which I have chosen for carrying out the research work, and the development of the process steps for the chosen open sources. And then I'll go through the research findings, their discussions, device characterizations, and then conclusion and future aspects. Now, coming to the background. So, if we see the solar cell market, if you analyze the solar cell market in the last decade, we can see that the use of silicon in the solar cell market is actually silicon covers 85% to 92% of the total solar cell market. And in this 90% of the silicon, 70% coverage is by polycrystalline silicon, and rest 30% is based on monocrystalline silicon. So why is it so? It's basically due to the advantages associated with anti-crystalline silicon wafers. The advantages are basically the avoidance of light-induced degradation. Generally, the conventional solar cells, which are based on p-type silicon, suffer from light-induced degradation. Their performance degrades when we keep the panel under illumination. It's because of the formation of boron-oxygen complex. But in case of n-type silicon, as the main dopant material, as the main substrate material is phosphorus, so there is no possibilities of having boron-oxygen complexes, and that's why the formation of light-induced degradation is not seen when we use anti-crystalline silicon. And also the minority carrier lifetime of n-type silicon is very much higher than the p-type silicon. And because the holes are the majority carrier in n-type silicon, and because holes are electrons mobility is higher than your hole mobility, and because of this, the recombinations in that when in that semiconductor material where hole is the dominant or the majority carriers, then again we'll see that the recombination is less. And when the recombination is less, and it will improve or enhance the carrier lifetime in that substrate. So and also it's seen that n-type wafers are more resistive to impurities. So and so there are certain advantages of n-type wafers. So that's why people are focusing on using n-type silicon in recent years. But the most of the solar cell technologies are based on p-type silicon. The technology is already established. So replacing the already existing technology with a new substrate based solar cell is a challenging phenomenon. And also, apart from this, there are other issues with n-type solar cells. And the most difficult part is the formation of p-type emitters with boron dopants. So why this boron diffusion phenomena is difficult in case of n-type solar cell? It's basically the atomic radius mismatch of boron and silicon, right? Boron is having around 0.8 Armstrong of atomic radius, and whereas silicon is having 1.14 Armstrong. So this atomic radius mismatch will result in crystal defects when we do the diffusion of boron in silicon. And also, apart from this, we will see the formation, in case of boron diffusion, we can see some formation of some boron precipitates on the emitter surface. and these are actually under boron research. These boron precipitates are also called boron rich layer, and these boron rich layer are actually act as recombination sites for the carriers in that are generated in under illumination. So this formation of boron rich layer is actually making the emitter no not like it actually decreases the suitability of emitter uses. So what in today's talk I'll focus on this part, like formation of this boron rich layer on emitter surface, how the different thicknesses of boron rich layer actually impacts on the device performance when we try to fabricate a solar cell with n-type silicon. And yes, people do fabricate n-type solar cells, but they use very sophisticated tools for the liquid dopant boron tribromide. And boron tribromide is very hazardous. So in order to handle that dopant source, we require extra safety precautions to handling the source. And when we use extra safety precaution, it increases the cost of production of the solar cell. So when we fabricate a solar cell, our basic purpose is to lower the cost of production while maintaining their efficiency. So it's necessary to see some alternatives, alternative dopant sources compared to the conventional boron tribromide dopant source, and that is why we tried to use some cost-effective dopant sources for our work, and these dopant sources doesn't require any kind of safety precautions as seen in the boron tribromide liquid sources. And um, uh, for the experimental work to be carried out, so we had used three dopant sources. Two of them are spin-on dopant sources, and other is the boron nitride solar source. And these spin-on dopants, in these two spin-on dopants, one is commercially available spin-on dopant source that is from Primtonics. That's a commercial company which provide boron spin-on dopant sources, and it has the boron dopant that is with some organic solvent, organic binders, and providers tell that generally say that it's a high purity dopant source, and but it has a few impurities present in that dopant source in the ppm level, like iron is there, sodium is there, tin, silver, and other impurities are there in that dopant sources. And other is the second dopant source is boric acid powder, and this boric acid powder is of 99.99% pure, but it's also having some different impurities in it according to the vendor. And another dopant source that is the boron nitrate solid source. This solid source is provided by Saint Gobain, and it is also said that the boron nitrate source is also 99% pure, but the impurities of that are present in that source is not provided by the vendor. So in order to use these dopant sources, we require a quartz furnace to carry out the process of diffusion, and we actually and the samples that there is a silicon wafers are generally placed vertically according to the vertically uh, vertically to the flow of the gases that are oxygen and nitrogen that are used in the furnace. And also, for the spin-on dopant cases, both the Primtonics dopant source and boric acid dopant source, they are basically spinned on the silicon wafer and then placed vertically in the slots of the quartz board that are placed inside the furnace tube. But in case of boron nitride solar source, we need to activate the source. Like first, the activation is done at 975 degrees Celsius, and these sources are according to the sizes of the wafers that we are preferring to use in that quartz tube. Like silicon wafer, if the size is 2 inch, then we need to cut the boron nitride solid source like size is made the same as to in silicon wafers, and those sources are placed also placed vertically, like as is seen in the figure. So this is the general process flow diagram which we use which we used in carrying out the experiments. So the experiment is carried out N-type silicon wafers. So it's both side polished wafers, and it's having orientation 100, and its resistivity is 1 to 5 ohm centimeter. So in order to remove the organic and metallic impurities present in that wafers in a ppm level, so RCA cleaning is done. So RCA cleaning is basically a cleaning developed by Radio Corporation of America long back in 1956, no, 1965. So these RCA cleaning techniques are used to clean the wafers that are used in our experimental work. So as we are using the anti-wafers, so it's very essential to form the ohmic contact on it. So like uh, generally for that purpose, and plus diffusion is very much essential. So for that purpose, we use phosphorus diffusion at the back side of the silicon wafers. So when we do the phosphorus diffusion, it actually forms phosphorus silicon, phosphorus PSD glass, and that glass is generally removed by dipping the samples into percent HF. So after the sample is properly cleaned and plus diffused, then according to the open source, the deposition or diffusion techniques are used. For like boron spin-on dopant, which is commercially available femtonic source, it's spined at 3000 degree or 3000 RPM, and then a baking step is required to evaporate the organic binders which are there in that dopant source. And in case of boric acid source, which we make the solution by using 2% weight by volume of boric acid in ethanol. And again, the spinning technique is same, but here we need to make the surface hydrophilic first, and then do the spinning. And then for boron nitride source, we do some activation of the process, dopant source that at 975 degrees Celsius, and then insert the samples uh, according at our then after ramping down to at 700 degrees Celsius, then we insert the samples, and then again carry out the diffusion processes at temperatures higher than 850 degrees Celsius. So this is how the emitter is formed, and in that process of depositing and diffusion. So when the rate of deposition or the amount of boron dopants present on the emitter surface is higher than the rate of diffusion of boron inside the samples during the emitter formation, then these boron precipitates occur on the emitter surface. So there are several techniques which we uh, adopt in the process itself. Like while ramping down of the diffusion process, it's a mandatory step to carry out in situ oxidation at 700 degrees Celsius for 20 minutes, so that the boron rich layer or the boron present in that precipitate from or in the boron rich layer will interact with that oxygen and form boron oxide, which can be removed by dipping it in 2% HF solution. So there are several techniques which will be discussing here. And As so depending on the dopant source, so the diffusion phenomena or the diffusion equations involved are mostly similar, but they looks little different, but and the equation is similar. So all these boron dopant sources which we use for our experiments, they are actually they form oxide, boron oxide during the process of diffusion, and in the diffusion process, and these boron oxides will react with silicon and then form silicon dioxide and boron. And silicon dioxide which are present on the surface actually will result in a glass on the emitter surface, and boron that gets diffused inside the silicon and from the emitter. So, so, so in case of boric acid, first it will form metaboric acid and water vapors. The water vapors get removed by the nitrogen flow that we are constantly using or blowing inside the quartz tube to maintain the inert atmosphere in the tube. So, and this metaboric acid result in boric oxide at around 250 degrees Celsius, and this boric oxide will result in silicon dioxide and boron at diffusion temperature, like generally at temperature 850 degrees Celsius or even higher. So this is how these equations are helpful in understanding the concept of emitter formation and formation of boron rich layer. So this is the schematic representation which will help us to understand how this boron rich layer forms. So this is our n-type wafer, and we did n plus diffusion at the back. And then suppose we have used some dopant source. It can be a spin-on dopant, it can be a boron dopant, whatever it is, that is there on the surface. So during the diffusion process, as you can see that it results silicon dioxide, and then silicon dioxide will, some part of it will react with boron and to result in borosilicate glass layer. And beneath this borosilicate glass layer, these precipitates are there that we call the boron rich layer. So these boron rich layers are actually these are insulating layers, and if such layers are present on the emitter surface, then emitter behavior will not be shown, and the device will behave as complete resistors. No generation of current will happen. So depending on the thicknesses of this boron-rich layer, the emitter actually will behave differently. And when we remove the borosilicate glass layer by dipping it in 2% HF solution, so this boron-rich layer generally doesn't get removed when we uh, consider the borosilicate glass layer removal step. So yeah, it's very essential to consider different other process steps where we can remove or lower the boron rich layer that is formed on the emitter surface. So what are the precautionary steps? So first is if we are using a dopant source, so it's very essential that the dopant source concentration is suitable so that it doesn't result a very thick boron rich layer on the emitter surface. That is the first thing. And when we carry out the diffusion process, it's an essential step to consider a in situ oxidation process during the ramping down of the diffusion process. So this ramping down would actually help to form boron oxide complexes on not boron oxide complexes and boron oxide ingot borosilicate glass layer, which can be later on removed by HF solution, 2% HF solution. And another, and suppose if the thickness of boron rich layer is very thick, like it's when I say very thick, it's generally more than 20 nanometer. So that is actually 20 nanometer is sufficient enough to lower the device performance. So When the thickness of boron rich layer is higher than 20 nanometer, then it's an essential to take some oxidation steps. So apart from in situ oxidation. So the chemical oxidation steps that is used is nitric acid treatment. So hot nitric acid when we use, then this nitric acid actually forms a oxide layer will form boron oxides on this reacting with that boron precipitates, and which can be later on removed by HF. So again, another treatment that is used for further higher thicknesses of boron rich layer, that is if it is higher than 38 nanometer or so. So a treatment that is used for this equal or uniform etching of the silicon surface that is used, and that is prepared with nitric acid, then acetic acid, and concentrated HF solution taken in the ratio 1:60:6. So these are some steps which are essential to be considered when we use some cost-effective dopant sources, boron dopant sources, especially the boron spin-on dopant sources that are commercially available, and also for boron nitride source. So now coming to this deposition steps. So when we do deposition, so as the commercially available crimtonic source is basically associated with organic binders, right? So and that's why it results a thick film when we try to deposit the dopant on the silicon substrate. So and basically the thickness varies depending on the RPM, or rotations per minute, of the dopant source. So generally, for our experimental purposes, we keep it at 3000 RPM. And in the process, you can also see the splitting of some dopant sources along the edges of the silicon wafers. And also, there are some patches of the dopant sources are also seen on the surface, and in other words, the surface doesn't appear to be uniformly deposited surface. It has some patches on it. While we use boric acid dopant source, boric acid generally gives a clear surface, so it doesn't show any kind of non-uniformity as seen in the commercially available spin-on dopant case. So these are the cases. These are the surface deposition pictures of ASEAN images of spin-on dopant sources. Generally, when we use boron nitride solid source, we don't see this kind of uh, like splitting and all, but boron nitride solid source is having other issues because of which its performance actually is not so high compared to these dopant sources. I'll discuss them one by one. So it's also after depositing the dopant source, it's an essential step to do the baking, to take the help of the baking step, because your dopant source, our dopant source is associated with organic binders, right? So when the organic materials are there, or elements are there, it's not suitable to use the sample in the diffusion formats. So as an essential steps, the samples are baked at temperature nearly 200 degrees Celsius for like 2 to 3 minutes or even more. And that is essential for both the spin-on dopant sources, like for spin tonics and your and our boric acid case. And so now when we analyze the surface after baking, we also see sometimes of minute cracks, like in case of textured surface where the pyramid height is average pyramid height is 4.5 microns. So there are certain cracks near to the valleys of the textures wafers. So these are certain kind of possibilities which can generate junction sorting when we use the spin-on dopant sources for forming diameter. So this can be considered as a drawback. And another drawback which is very essential, so it to consider actually when we after baking when if we keep the samples like in the ambient condition or in the lab condition for more than 10 minutes. Then again, the boron which was there in that theme will react with the oxygen that are present in the ambience and will form some powder kind of structures on the sample itself. So these are actually boric acid. That boron gets converted to boric acid by absorbing the moisture present in the ambience condition. All these experiments were carried out in under clean room conditions. So clean room, the humidity and temperature, everything is maintained. But even in that ambience also, we could see the moisture trapping phenomena and resulting some powder-like structures uh, on the uh, sample surface. And if we insert these uh, samples in the quartz furnace, definitely it will generate non-uniformities and also it will make the junction sorted. So it's an essential, it's very essential to insert the sample immediately just after baking the uh, samples after depositing the spin on document sources. So when we and yes, when the samples are kept in the furnace and their essential steps are, as I have already told, that the diffusion is carried out uh, for a particular period of time, like 10 minutes, 20 minutes, and even more, according to our required junction depth. And when we do the diffusion, and then again during the process of ramping down and into oxidation is to be used in the process, so that the formation of boron complexes in the sample gets lowered. So how does it appear? Like how we can identify the formation of boron rich layer on the surface. So when we used Primtronics dopant sources, then we will see that boron rich layer, which are formed or which are seen after removal of the borosilicate glass layer, they will have some brown color, dark brown color, and these brown colors, colored precipitates generally do not go away when we treat them in 2% HF solution. And uh, but in case of boric acid case, we generally do not find any such patches or any such colors, even though the formation of boron-rich layer on the surface appears to be higher, like uh, when it is higher than thicker than 20 nanometer, even though we cannot see any color on the surface. But yes, another property of boron-rich layer it is hydrophilic in nature. So water gets sticked on the surface, and because and that is why we cannot have a hydrophobic surface for carrying out further experiments or further process steps for fabricating the whole solar cell. So, depending on the sources used or depending on the diffusion conditions that we are using to make or form the emitter, we can see the different properties or different formation styles on the emitter surface. And in case of boron nitride solid source, we do not see any kind of that actually appears to be very clear. And yes, in certain cases, the sample shows hydrophilic nature, but in most of the cases, the formation of boron rich layer are actually less than 10 nanometer or nearly about 10 nanometer, which is less compared to this boron spin on dopant sources. So this is the general structure which is seen under TEM analysis. And in our case, we could see that the boron rich layer which was getting formed was not uniform in thickness. So at certain region it was 50 nanometer, and in at other regions it was 10 nanometer. And we actually we did some SIMS analysis of uh, these samples. Like when we do SIMS analysis, secondary ion mass spectroscopy analysis, it gives us the junction depth. And if the boron rich layer or boron precipitates are present on the surface, then we can see some peak uh, concentrations or higher concentrations of the dopants on the emitter surface. Generally, uh, on the emitter surface, the concentration uh, are uh, now 8 or 9 to the power 19. But when the precipitates are present, then the concentration goes up to 20, of the order of 22. And when we analyze the boron rich layer, so depending on the thickness, we can see the constituents of the boron rich layer actually varies depending on the thickness of the boron rich layer. So XPS analysis was used to determine the concentration, and we could see that with increasing thickness of boron rich layer, the amount of oxide in the boron oxide complexes will decrease gradually, but the boron concentration will increase. And also the contact resistance, which is done by TLM method. So it was showing that with the increase in the thickness of boron rich layer, the contact resistance of the boron rich layer uh, also increase. So these are uh, so uh, so these are generally this analysis was carried out with Primtonics dopant sources, because in that Primtonic dopant source we can see the presence of boron rich layer on the emitter surface, and we can when we do or apply any treatment to remove them completely from the surface, it was visible and it was detectable. So all these analyses to determine the properties of the boron rich layer were carried out by using Primtronics dopant sources. But under the same diffusion conditions, and if we try to analyze the boron rich layer formed in the boric acid case or the boron nitrate solid sources, so these properties might vary. And yes, we have tried different concentrations of boric acid solution and also the boron spin on dopant case. So for boric acid solution, we could see that 2% boric acid actually gave the um, best results, which didn't result any kind of boron rich layer formation in the diffusion process when carried out under the same diffusion conditions as seen in Primtonics dopant source and others. And if we analyze the seed resistance values of the dopant sources, then we, uh, we see that when the boron rich layer is present on the emitter surface, it actually lowers the seed resistance. And uh, when the boron rich layer is removed, the seed resistance value gradually increases. And also another important phenomenon which is seen in case of very high thicknesses of boron rich layer that are present on the emitter surface. So when the thickness is higher than 50 nanometer, some kind of surface defects are seen on the emitter surface. So these defects are basically due to the mismatch in the thermal expansion coefficient of this boron rich layer and the silicon when we consider the high temperature processes. Generally, the diffusion processes are carried out at temperature more than 850 degrees or so, and in situ oxidation again it's at 700 degrees Celsius and so. So when we have this type of thick boron rich layer on the surface, then some kind of defects, permanent defects, we can say, are seen on the emitter surface, which is not at all desirable for the cell performances. And we need to consider to lower the boron rich layer below 20 nanometers so that such types of defects are not seen on the emitter surface after the process of diffusion. And another important thing is the measurement of bulk carrier lifetime. When we say bulk, actually the carrier lifetime, when you measure it, it gives us the effective carrier lifetime. That is the combination of the lifetime of the surface and the bulk. Actually, it is the bulk which is responsible for all the solar cell performance. So that's why we need to carry out, or we need to measure the bulk lifetime for the devices, and you need to see how this bulk lifetime varies when we use different types of dopant sources and under for different purposes. And we could see that when boron and also this is an important this is important to say that when we carry out the bulk lifetime measurements, it's not on the CZ wafers, it's on float zone wafers. Float zone wafers are high purity silicon wafers. The other properties are the same, the MTech 100 orientation and 125 resistivity, but the type of the wafers are float zone wafers. It's a high purity silicon wafers. So the in order to see the bulk lifetime changes when you do the boron diffusion, so those wafers are used. So we could see that bulk lifetime actually it decreases when we increase the diffusion temperature, and the bulk lifetime for textured surface is even lower. And also the bulk lifetime of the sample it actually decreases with the increase in boron rich layer thickness on the emitter surface. So this is how the bulk lifetime is getting affected when with the increase in the thickness of boron rich layer. So yes, other property is like emitter saturation current measurement, and emitter saturation current actually tells us all the recombinations that are leading to lowering the degradation of the device performance. And we could see that with the increase in the boron rich layer thicknesses, the leakage current in the device will also increase. So, yes, there are certain methods by which we can lower the formation of boron rich layer when we consider the spin-on dopant sources, especially the Plimptonics spin-on dopant source. So, what is that? When we do the before depositing the samples, before depositing the dopant sources on the silicon wafer, if we use some 5 nanometer of thickness on the emitter surface, then you could see that the device performance actually it gets improved by some values. So in case of spin-on dopant case, we saw that the efficiency was in some cells it was 6.6%, but after using the 5 nanometer of oxide layer on it, so the device performance for the same for the samples with all the diffusion conditions and all the process steps parameter actually got improved to 9.5%. And in that's why it's we can say that some kind of this kind of oxide layer actually helping the or preventing the emitter for getting sorted during emitter formation. And in case of boric acid case, we could see the efficiency for the same diffusion conditions was 8.8%, whereas the simulated results were showing the best efficiency that we could achieve in these cases uh, is 15.44 percentage, but the formation of with all this process steps um, issues and boron rich layer formation actually lowered the experimental efficiency value. So this is there. And yeah, let us compare the results of all the dopant sources that we have used to carry out the experiment. So as we see that different boron-rich layer formation the thickness their thickness and their properties actually vary depending on the dopant sources, and for the same diffusion condition, we could see that boron nitride sample actually gives a higher junction depth compared to that of spin-on dopant sources. And if we measure the other parameters like bulk lifetime and all, so we could see that boron nitride diffuse samples are having the lowest bulk lifetime values compared to that of other samples, and it has the highest saturation current density, even though we do not see the detectable boron-rich layer on the emitter surface. And uh, the solar cell performance, if we see for the emitter resistances, seed resistances value, for average seed resistance value 45 ohms per square. So if we see, then the best result is obtained for boric acid diffused sources, and then Primtronics boron spin-on dopant sources, and the lowest performance was seen for boron nitrate solid sources. So this is the all that uh, I have for today's discussion. And yes, we could see that boron-rich layer is a phenomenon so which is not desired in emitter formation, and it's very essential to lower the formation of boron rich layer on the emitter surface by different process steps. And yes, we had also seen that a thin oxide layer, like in between 5 nanometer to 10 nanometer, actually improves the device performances. And among all these dopant sources, boric acid was giving us the best result. It was also it was the cheapest of the cheapest dopant sources that uh, among all the dopant sources that we have used in our processes. So depending on the dopant sources, we can have different boron-rich layer thicknesses on the emitter surface, and also their properties differ uh, depending on different dopant sources. And people are constantly trying to use the boron, other aspects of boron rich layer. They are trying to use it as gathering sites for improving the performance of the solar cells. And also for if we want to use these solar cells for wide applications in coming years for making a commercially available solar cells, then we need to optimize the cost and without no, no, lowering the efficiency of the solar cells. So these are some future aspects that we need to consider when we try to use the cost-effective token sources. And these are some of the publications related to this work, some journal publications and some conference papers. And also this work was actually carried out under guidance of Professor Sadhan Singh Solanki. And so I want to acknowledge them all who helped me while carrying out the experiments. Uh, and also the labs like National Center for Solar Photovoltaic Research and Education, NCPRE, then CEN and SAFE facilities, and also for SIMS analysis, SSPL Delhi actually helped me a lot. So yes, this is